Okay, part two, we got to do these story problems. Everybody's favorite. There are going to be two story problems on the test. Two story problems from chapter 5. Now we notice the first one deals with money. It deals with an investment compounded continuously. The formula that we learned for that is the amount after a certain time t is equal to the principal, that's the amount initially invested, times e to the rate times time. Okay, this is a formula that you're going to have remembered for the test. This will not be given on the test. You have to remember, most students just remember the phrase Pert, principal times e to the rate times time. Now you also have to know what they're asking. They're asking for how long would it take. So what part of this formula are they asking for? They're asking for t. We need to solve for t. As long as t is an exponent, we can't solve for it. So this is going to involve logarithms so that we can make t no longer an exponent. So let's fill in what we do know. We know an initial investment was $5,000 times e. We know the rate is 0.06. We don't know time. That's what we're solving for. Now, they also didn't give us an ending amount, but they want this to double. They're asking how long would it take for this to double. Well, if $5,000 doubles, then our ending amount is going to be $10,000. Now this is an exponential equation. To solve an exponential equation, we need to isolate the exponential term. This is the exponential term right here, e to the 0.06 times t. So we need to divide by 5,000. That's going to be 2 equals e to the 0.06 times t. Now we need to use natural logs because the natural log cancels a base of e. So if I take a natural log on that side and a natural log on this side, then on the right side we're left with 0.06t equals the natural log of 2. Now remember, we're solving for t. T is being multiplied by 0.06. So we divide by 0.06 and our final answer is t equals the natural log of 2 divided by 0.06. Since we don't use calculators, we leave it in this form. Okay, if we were using calculators, we would have to figure out what this approximately equals, how many years. But this is how we leave it. Okay. Now 34 and 35 are both examples of exponential problems, exponential growth or exponential decay. So they're actually both going to use a very, very similar formula to this one, the Pert formula for continuously compounded interest. The formula is the amount after a certain time or at a certain time, a sub 0. Now a sub 0 just means an initial amount. It's very similar to the principal. They just call it principal because that deals with money. A sub 0 is a starting amount. Then we times that by e to the k times t power. So it is essentially the same formula as this. They're just different letters. T stands for time. K stands for what's called the growth rate or the growth factor. It's a percent of how quickly the quantity is either growing or decaying. So it's very similar to an interest rate. So in 34 we're dealing with bacteria culture that starts with 10,000 and it doubles every 40 minutes. So this is an exponential growth problem. Okay. What they're asking us for is to find a function that models the bacteria at time t. Now we have a formula right here, but in order to make it into a function there only can be one unknown, and the unknown that we want to have is t, because this needs to be a function of t, of time. So in order to make a function now, we need to find out an initial amount and our growth factor so that we can write this as a function. So what do we know? We know an initial amount this 10,000 bacteria times E to the KT, and that equals A of T. All we know right now is an initial amount. We don't know the growth factor. So here's what we need to do. We need to find a value of K so we can plug this back into this formula to end up with a function of T. So in order to solve for K, that means that K needs to be the only unknown, which means we're going to have to use some value of T and some ending amount in order to leave K as an unknown. Now, this is telling us that every 40 minutes, the number of bacteria doubles. So if I put at 40 in for T, after 40 minutes, 10,000 bacteria are going to have grown to 20,000. So now we have some kind of an equation here that's going to allow us to solve for K. Once we know the value of K, we can plug it back into this formula and end up with a function of T. So K is an exponent, which means we're going to have to use logarithms to solve for it. This is very similar to what we did over here for this problem 33. Divide by 10,000 to isolate the exponential term. We're going to have 2 is equal to E, to the K times 40. Now we take natural log on both sides to cancel the exponential base there. So we have the natural log of 2 equals K times 40, divide by 40. And now we know the value of K is the natural log of 2 over 40. So to finish this problem, the amount is equal to the starting amount times E to the natural log of 2 over 40 times T. This function will allow us to make predictions on the number of bacteria at any value of T. We could now answer questions such as how much bacteria would there be after 4 hours or after 12 days. You know, we have a function now that we can plug in a time value, and it will allow us to figure out how many bacteria there are. So here is the answer. 35 is very similar, except now we have half-lives. So after 140 days, a 300 milligram sample is going to be reduced to 150 milligrams. It's getting cut in half. So this is an example of exponential decay. It uses the exact same formula, however. A of T equals an initial amount times E to the KT. And they're asking us to do the exact same thing. Find a function that models the amount of the sample remaining at time T. So we need to make a function where T is the only unknown. Kind of like here, where T is the only unknown. So that's going to involve finding our K value because they didn't tell us. So let's see, we have an initial amount of 300 milligrams times E. We don't know K, that's what we're solving for initially. Now we know that after 140 days, which is a time value, so 140 days, there's going to be half of the substance remaining, so this is 150 milligrams after 140 days. Now we need to isolate this exponential term so we can solve for K using natural log. So we divide by 300. We're going to get 1/2 equals E to the K times 140. Now we need to use natural log to cancel the base so we can solve for K. Natural log on both sides. So we have is the natural log of 1/2 all divided by 140 is our value of K. So our function now, we go back up to this formula to help us write our function. The amount at a certain time is going to be 300 times E to the natural log of 1/2 or 140 times T. That is it. That is the end. Good luck.